The final category of buffer overflow style attack we will consider is called a format string attack. It is named for the format strings used by the printf family of library functions in the standard C library. A format string is typically the first or one of the first arguments to a printf style function, and the remaining variable number of arguments comprise the data to be printed. Format strings use what are called format specifiers to indicate how data should be formatted. For example, the code snippet shown here prints out a record consisting of an individual's name and age. The first format specifier applies to the first argument following the format string, and the second specifier applies to the second argument. In this case, the first argument is a string and the second is an integer. There are also many other kinds of specifiers too. Now let's see how a simple misunderstanding of how format strings should be used can lead to a serious vulnerability. Now, we might wonder, what's the difference between this function and this function? We can see that on the first two lines, the functions are identical. They allocate a character buffer on the stack, and they call fgets to read into it. The difference is on the third line. The first function calls %s as a format string prior to printing buff, whereas the second function forgoes using a format string altogether and just places buff there. Now, we might think to ourselves, buff is just a string in both cases, so why do I need the format string? Well, the important part is that buff might itself contain format specifiers. In the first case, if it does, those specifiers will just be printed out to the screen. In the second, those will be interpreted. If the attacker controls the format string, then the interpretation of those format specifiers can work to his advantage. So let's look at how printf is implemented and see how that might happen. Here we see a call to printf. It's going to print out I and its address using the %d and %p format specifiers. The first is for printing an integer, the second is for printing out a pointer. Here's what the stack might look like, with the topmost address range to the right and the stack growing from right to left as usual. We can see the arguments on the stack. First of all, the %i argument, the I argument, and the format string, pushed in reverse order. Printf takes a variable number of arguments and pays no mind to where the stack frame actually ends. It presumes that when you called it, you passed in at least the number of arguments specified in the format string. Here we have %d, which corresponds to the argument 10, and here we have %p that corresponds to the argument %i, so everything is well. Now let's go back to our vulnerable function. Suppose we passed in the format string %d %x, and notice that there are no additional arguments provided. In this case, the stack will look as follows. We'll have just pushed the format string argument, and that's all. Now when printf goes to interpret that string, it will read from the caller's stack frame the %d portion, and then will read again for the %x portion. Let's think about some other format strings and what might happen. This format string will print out the 4 bytes above the saved instruction pointer. Why is that? Well, it turns out that printf ignores any spaces between the % and the format character that's used in the specifier, in this case %d. In this case, it's going to print out the bytes pointed to by this stack entry. So it's going to look one past the saved EIP, interpret that 4 bytes as a pointer, go to that memory address, and then print out the entire contents until it reaches a null terminator. This will print out a series of stack entries as integers, and this format string will print them out as hex. Now here's the really terrible one. This one will actually write the number 3 to the address pointed to by the stack entry. Why is that? Well, %n is a format specifier that is used to write the progress that printf has made in printing out to the output stream. In this case, it will have printed 3 characters, 1, 0, 0, and so it will print the number 3 to whatever the argument is on the stack. It's expecting to receive an integer corresponding to the %n, but it's not actually going to get one. Instead, it's going to overwrite the stack entry instead. And as you might suspect, this is going to allow the attacker to do a remote code injection in certain circumstances. So you might ask yourself, why is a format string attack like a buffer overflow? Well, we should think of it as a buffer overflow in the sense that the stack itself can be viewed as a kind of buffer. That is, all of the arguments defined by a function define a kind of buffer and bounds. The size of that buffer is determined by the number and size of the arguments passed to the function. So providing a bogus format string thus induces the program to overflow the buffer as defined by the arguments. This vulnerability has been around for quite a while and continues to happen despite people knowing about it. Now that we have seen the wide variety of buffer overflow style attacks that exist, it's time to trade our black hat for a white one to see about how to defend against them. In our next unit, we will step back and look more carefully at what these attacks have in common. Then we will look at a variety of different defenses and evaluate their effectiveness. In essence, we will chronicle the cat and mouse game played by attacker and defender over the last couple of decades. By the end, we will see that, unfortunately, when programming in C, the attacker still largely has the upper hand. Fortunately, it is far more difficult today to generate an exploit than it used to be, and new methods for avoiding buffer overflow vulnerabilities are being developed.